Welcome! We have developed the content for this course in the past 6 essentials. In this essentials finale, I address a number of special topics that deserve your attention. Except for the first, these topics relate to the practical aspects of working with the discrete Fourier transform. The learning goals for today are the following ones. First, understand why the discrete time Fourier transform sometimes contains Dirac impulses. Second, understand what we mean by circular extension of signals when using the DTFT. And third, the effect of circular extensions, namely circular convolution and spectral leakage. Fourth, understand the use of zero padding and temporal windowing to overcome the artifacts of circular extension. And then fifth, the use and trade-offs in designing the impulse response of FIR filters, starting from the desired frequency response. And finally, how the DFT can be efficiently implemented as a FFT, Fast Fourier Transform, by exploiting the structure of the DFT equations. Let me start with a peculiarity of DTFTs when dealing with discrete time signals that contain harmonics, that is, pure sinusoidal signals. Here is the DTFT amplitude spectrum of a signal that contains, first, a typical broadband component composed of many different frequencies, like we have in speech or sensory information. And second, it also contains two sinusoidal components at the frequencies omega is pi over 4 and pi over 3. You see that the DTFT values x of e to the power j omega are indicated with an upward pointing arrow, symbolizing that we're dealing with so-called Dirac impulses or Dirac functions on these digital frequencies. You may wonder why we use these funny symbols to denote the sinusoidal components in the DTFT spectrum, rather than just doing this, plotting the DTFT value at the two frequencies. Well, the answer is that this drawing might be intuitively okay, but it is mathematically incorrect. Let us consider a simple case. We know that by Euler's equation we can write this discrete time cosine as a sum of two complex exponents. This looks like a DTFT, so it is tempting to write x of e to the power j omega in the following way and to plot the magnitude spectrum as suggested earlier. Now let us calculate the inverse DTFT on this result. This simple integral over a constant of course returns the result 0, because the lower and upper integral bounds are the same. You might think, let us slightly change the lower and upper bound by an epsilon value. But that will introduce frequency components that are not part of the signal at all. And if we let epsilon go to 0, the result of the integral will become 0 again. The correct way to calculate the DTFT is to use the definition and work through the different steps. I will not elaborate here, but the result is that we obtain a DTFT of infinite value at the frequencies pi over 4 and minus pi over 4. The infinite value is, however, such that taking the limit of this integral, we get exactly the value 1. This mathematical construct is called a Dirac function or Dirac impulse. So these two figures look more or less the same, but when it comes to the DTFT, the one on the right is the correct one. In practice, we naturally use the DFT. In that case, we just have the complex amplitudes for each digital frequency that the DFT can represent. For example, in this particular case for n is 512, the DFT magnitude spectrum looks like this, with non-zero values for k is 64 and, of course, k is 448. The second topic I want to discuss has to do with the periodic nature or circular extension of the DFT in the time domain. We already know that the DTFT x of e to the power j omega is periodic over 2 pi, and as a consequence that the DFT x of k is periodic over the number of samples n over which the DFT is calculated. However, a direct consequence of sampling the DTFT continuous frequency axis is that the signal x of n is implicitly assumed to be periodic over the n sample values. Or, put more correctly, we have to assume that x of n is periodic over n samples in order to be able to represent it with a finite set of complex exponents, each with a digital frequency that is a multiple of 2 pi over n. In a way, this is similar to the Fourier series, where we had periodic continuous time signals with frequency components consisting of multiples of the fundamental frequency 2 pi over t. Now, if I say that xn is assumed periodic, it means that in any calculation we perform with the DFT, we assume that copies of the signal are connected to each other, head to tail. We also call this circular extension of the signal, because head and tail appear to be circularly connected. This is not something we choose, but a result of working with the DFT, always, not only here, but for every application of the DFT. The circular extension when using the DFT has two consequences. The first one has to do with the boundary effects of convolution. Let us revisit the convolution example of the previous essential. Here is the impulse response and the signal that we have considered. Note that the last sample x15 was taken as 0. The reason was that at the time I did not want to complicate the explanation of the convolution theorem with circular extension. So now let me change the signal value x15 to, let us say, minus 5.5. If we take the DFT of the impulse response h, the signal x, multiply the two and do the inverse DFT, this is the result. Now if you do the convolution in the time domain, this is the result, and these two results are slightly different. The cause is that for the calculation of y0 we need x minus 1, which we took to be 0 in the time domain convolution, giving y of 0 is 8.18. But the DFT assumes that the signals head and tail are connected, hence x minus 1 is x15. Thus the convolution uses the value minus 5.5, yielding y of 0 is 13.68. Of course, this effect gets worse as the order of the filter increases, that is, the number of samples used in the convolution. It is therefore important to realize that if you do convolutions through the DFT domain, you obtain the result of what is known as a circular convolution. If you do the convolution in the time domain, you calculate a linear convolution. We try to reduce the unwanted difference between linear and circular convolution by a process known as zero padding. That is, adding zero value samples to the head and the tail of the signal. For instance, we can add a couple of zeros like this. If we now calculate the circular convolution using DFTs, we get this as a result. Obviously, the appropriate length of zero padding depends on the order of the FIR filter. A second consequence of the circular extension of signals has to do with an effect known as spectral leakage. Consider this harmonic signal, cosine of pi over 100 times n over 1000 samples. As this is a pure cosine, the DFT amplitude spectrum we would expect has a non-zero value at digital frequency pi over 100 or k is 5 in the DFT. However, if we take a slightly shorter segment of the signal, like here, 920 samples, the amplitude spectrum looks like this. We still see a peak around k is 5 or omega is pi over 100, but with many other surrounding non-zero DFT coefficients. The explanation is, again, the circular extension. In a way, the DFT sees a signal like this, which is far from a pure cosine, because of the discontinuities at the boundaries of the signal. As a result, frequency content spills over from the pure harmonic signal to neighboring frequencies, hence the name spectral leakage. This is of course an undesirable effect. The most common way to reduce spectral leakage is to avoid the boundary discontinuities. This can be done by smoothing the transition between the signal values at the head and tail, for instance by applying a temporal window such as this Hamming window. Each sample is multiplied by a factor that gets closer to 0 at the head and the tail of the signal. This means that the signal we now analyze through the DFT looks like this. It is clear that the resulting amplitude spectrum shows reduced leakage, but at the same time the peak has become less pronounced. Suppressing spectral leakage generally results in the loss of accuracy with which individual signal frequencies can be identified. In other words, we have to trade off spectral leakage and spectral resolution. In the third topic of this essentials, the design of FIR filters, we also need to deal with the circularity of the DFT. The desired behavior of an FIR filter is often described in terms of its frequency response. For instance, to remove certain frequencies by a bandpass filter, to amplify certain frequencies, or more intricate ways of changing the frequency content of a signal. By specifying the DFT coefficients of the frequency response, we of course also define its impulse response. Let us say we want to design a bandpass filter for frequencies between 0.7 and 1.4 radians. The magnitude of the DTFT frequency response then looks like this, and the DFT like this for the case of n is 256. The phase is more difficult to choose, so let us just start assuming zero phase everywhere. If we then carry out the inverse DFT, this is the impulse response we obtain. Two effects are worth considering. First, we get an impulse response of 256 non-zero values, that is, 256 non-zero filter coefficients. In many cases this is undesirable for real-time performance or quality reasons. We therefore want to limit the length to, let's say, 20 to 30 non-zero filter coefficients. Second, we observe the consequence of the circular nature of the DFT, because the impulse response coefficients for negative n are found at the tail of the computed inverse DFT. So the actual impulse response that we're looking for is this one. Let us deal with these two issues at the same time. First, we limit the length of the impulse response to 31 coefficients. This of course affects the magnitude of the filter's frequency response. To limit the spectral leakage that would be caused by simply truncating the impulse response, we apply a temporal Hamming window. And second, we right shift the impulse response by 15 samples. This only affects the phase of the frequency response. After all, we know that a system that delays a signal over n samples has an impulse response of delta n minus 15 and a frequency response of e to the power minus j omega times 15 for the DTFT, or e to the power minus j 2 pi over 256 times 15 times k for a length 256 DFT. In other words, two neighboring DFT coefficients differ in phase by 0.367 or 0.12 pi radians. Here is the resulting frequency response of the adjusted impulse response. Indeed, we now get an approximation of the desired bandpass filter. And we also see that the phase decreases linearly with 0.12 pi radians per DFT coefficient, with phase wrapping at minus pi. I think you understand that there is no unique solution to this filter design problem. The order of the filter, the spectral leakage and the spectral resolution must be traded off. All signal processing software packages include procedures in which you can specify your frequency response preferences, and the filter coefficients are then found through numerical optimization procedures. The fourth topic of this Essentials is the efficient implementation of the DFT. Going back to Essentials 6, we know that the time domain convolution in the top part of this diagram can also be implemented by the product of the DFTs in the bottom part of the diagram. Let us consider the complexity of the operations. For that we take a worst case scenario, namely that both the signal xn and the impulse response hn have n non-zero values. The direct convolution in the time domain then takes n squared multiplications and additions. Since multiplications are computationally more expensive than additions, let us say that we have complexity n squared. For the bottom part we need to calculate 2 forward and 1 inverse DFT, or, since the equations of the DFT and the inverse DFT are nearly identical, let us say that we need 3 DFTs. We also need to calculate the product of n complex numbers, namely the DFT of x and the DFT of h. The latter obviously has the complexity n. Now what is the complexity of the DFT? We have seen in Essentials 5 that the DFT is in fact an n by n matrix vector multiplication, which has n squared complexity. So overall we end up with 3n squared plus n multiplications, which is actually larger than what we had for the time domain convolution. Now fortunately efficient implementations of the DFT, known as Fast Fourier Transforms or FFT, exists. And those implementations require only n log n multiplications, not n squared. For that reason, applying the convolution theorem by going via the bottom part of the diagram is computationally much more efficient. Here's an illustration with actual code. For maximal intuitive feeling, we take n really big, namely 500,000. We fill a signal and an impulse response of that length with random numbers, and we calculate the convolution in the time domain. And we wait. And we wait more. You see that this operation takes tens of seconds. Now if we carry out the convolution in the DFT domain, it takes less than 50 milliseconds. So taking the long route does pay off, but only because the FFT exists. The DFT can be implemented efficiently as FFT because of the special structure of the DFT equations or DFT matrix. Remember, the factors by which the signal samples are multiplied in the DFT equations are all powers of e to the power minus j 2 pi over n for varying k and n. For n is 2, we obtain this matrix, showing that the two DFT coefficients are just the sum and difference of the two signal samples x0 and x1. For n is 4, we obtain this matrix, which can also be written like this if we interchange the positions of x1 and x2. Now in this 4x4 matrix you can easily recognize 4 submatrices, each of which is a variation on the 2x2 matrix for n is 2. In fact, this matrix structure can be exploited in a signal processing flow diagram. You see two 2x2 DFTs and one combination stage with appropriate multiplication factors, also called twiddle factors. We can repeat this process for n is 8, which gives us a familiar butterfly diagram. For a DFT of arbitrary length n, we get in this way log 2n stages and per stage n multiplications for an overall complexity of n log n. There are many variations on this butterfly structure, for example if n is not a power of 2. But in all cases the complexity is reduced from n squared for the standard DFT expression to n log n for the FFT implementation. Then, as a final topic, I like to address the following. In practical applications, we often analyze signals in so-called spatio-temporal frequency bands. This term refers to the fact that we consider the DFT results of temporal segments of a signal in certain frequency ranges. In terms of the temporal segment, we divide the signal in sufficiently short time intervals, so that we can assume that the properties of the physical system that created the signal, for instance a vocal tract, music instrument, a biological system, does not change too much. In other words, we assume that in the sufficiently short time segment, the underlying physical system is LTI, linear and time invariant. Time segments can be disjunct or overlapping, and in many cases we apply temporal windowing, for instance using a Hamming window, to avoid spectral leakage. The resulting DFT coefficients within each time segment are then aggregated in so-called frequency bands. This means that we add the magnitude of the DFT coefficients of adjacent frequencies, for example according to a perceptual model. One such model is the MEL frequency scale, where DFT coefficients are grouped into 24 bands tuned for human speech recognition. Different frequency scales exist for other applications, and sometimes the frequency bands are also relatively weighted to further account for perceptual characteristics. From this you see that convolution using the DFT is fairly straightforward, of course not forgetting the circular extension. But also that the use of the DFT for signal analysis is often only a first step, after which many more analysis and possibly machine learning steps will follow before the final result is obtained. And that is how computer scientists see signal processing and the DFT. It is a great means for efficient FIR filter implementation, and it also provides us a means for characterizing a signal in terms of its frequency content to be used for recognizing, understanding and predicting the content of all sorts of signals. So, here we are at the end of the course. I hope that you have enjoyed the explanations and examples in the essentials, along with, of course, the recorded lectures on Collegiorama, the theory exercises and the Python examples of signal processing theory and applications. I wish you every success with the further study of the course materials and the exam. I hope to meet you again some other time. I say so long.